So now that we're experts on the dot product, let's talk about variable force, because all of this we've been talking about a constant force. But can you think of a force that varies over distance that we're familiar with?
Gravity.
Gravity changes with distance. We haven't talked that much explicitly about these, but springs, right? If you stretch a spring more, it has more force. If you stretch it less, it has less force. So these are both variable forces. So we'll start out with a very general case. So here's a graph of a variable force. So this is the force on this axis. This is your displacement or position on this axis, okay? So remember, in this case, we're going to say that because this is F sub x, what does that mean about the force?
In the x direction.
It's in the x direction, which means these are inherently, we're not dealing with angles right now. X and Fx should be pointed in the same direction, okay? But what we are dealing with is a force that changes at each point, okay? So since work is force times displacement, we can rewrite work, and is this force constant? No, right? We can rewrite work as an integral. So that means at each point, you take the dot product of force and the position, but then you have to add them all up. And what does that mean if you're actually looking at this? Let's say we want to know, so this is your limits, right? If we want to know the force or the work done from one position to another, what do? What does it look like to take an integral of this? So let's say we want to know the force, the work done between these two positions. Here's our initial position, here's our final position.
Find the area under it.
You just find the area under the curve, okay? So this is your work, all right? It's the area under the curve of this variable force, okay? And now this still has a dot product, so if you had a force that had multiple directions that are not just x, it gets a little bit more complicated. But for our purposes, we're going to try to stay in one dimension for this, okay? All right, but I'm just warning you because if you go on in physics or engineering, sometimes you have more complicated situations than just f sub x and x, okay? So there's both a possibility for this to vary and for these things to be non-parallel, all right? Okay, so speaking of our variable forces, a spring is a variable force by definition, okay? A spring exerts something called a restoring force whenever it's either stretched or compressed. And what that means is, let's say these are all at what we call the equilibrium length. Because remember, this x, or s in this case, is a delta, it's a displacement, and it's a displacement from your equilibrium length. So if you just have a spring sitting there and it's not pulled or pushed, right, it has a particular size. That's your 0. For this situation. So we'll call that x equals 0. So here's an unstretched spring. What we mean by restoring force is that, oh, and also K is this spring constant, right? So it just gives you sort of the what is that called? The stiffness of the spring, okay? So bigger K means harder to stretch and compress. Smaller K means easier to stretch or compress. All right, so a stretch spring would look something like this. You've pulled out the spring, and that means your displacement goes in this direction. You've gone from this unstretched value to this stretched value. That's your displacement. It's pointing this way. Which way does the force point? The other direction, because if you let go of the spring, what does it do? It goes back that way. Okay, so that's what we mean by restoring force, and that's what this negative sign means, okay? This gets very confusing when we start doing force diagrams because if you draw it correctly, you don't have to include the negative sign, but the negative sign does tell us that if we have a displacement, the force points in the opposite direction, okay? So if we compress the spring, okay, obviously we have a displacement in this direction, and then the force should go in the opposite direction. So, if we want to sort of plot this, if we want to plot our spring force over displacement, it actually, what would it look like? So if you go in the negative direction, what kind of force do you expect? Positive. So if you're over here, you should, as you go farther out here, you should have a large positive force. And as you come in closer, it should get smaller and smaller because you're compressing it less and less. Once you get to here, if you go into the positive value, that means you have a negative force, okay? So it's linear and it looks like this, all right? Let's say we wanted to figure out the work done to to compress the spring from here to here. What do we do? Oh boy. Okay, it's back. So what do we do to calculate the work done by the spring? Find the area under the curve, okay? So you would just go like this, okay? And if you want to figure out the value here, it's just going to be kx max. That's the value of your force, okay? So, and what's the area of a triangle?
1/2 base times height.
Yeah, 1/2 base times height, okay? And here's the thing. 1/2 base times height gives you a value under this curve of, so this height is kx max. This base is x max. So you end up with 1/2 this times this. So it gives you 1/2 kx squared, which it turns out is the potential energy of a spring, okay? So we'll get to that in a second, but let's try doing this as an integral, which is fun. I know I promised you less integrals, but I was wrong. This chapter has a couple. But they're mostly derivations and you don't have to do them yourself. So you stretch out a spring with constant of k equals 50 newtons per meter. That's our spring constant. And by 50 centimeters, we want to know how much work the spring does to return itself to its natural length. So essentially, if we want to draw the spring, we take a spring, here's our x equals 0, and we stretch it out to x equals 50 centimeters. What is the displacement? Which way does the displacement point?
That way.
It points this way, but when we're looking at the actual problem, what is it asking for? Which it's going back to its equilibrium length. So we actually are talking about a displacement that goes this way. So this is our delta x. Which way does our force point?
The opposite direction.
This way.
So over here, it's pointing this way, right? And as it gets back to equilibrium length, the force should get smaller and smaller, but we're only going to draw it this one time. But you'll notice this is a variable force, right? Because as x gets smaller, force also gets smaller, okay? So we want to look at our definition of work. And our definition of work, the full definition of work, is going to look something like this. It's going to be F dot dr from R initial to R final. Okay, this is our definition of work. Okay, in this case, what is our force? Do you remember what a spring force is?
Oh, it's negative spring constant times change.
Yeah, negative, in this case, we'll call it kx because we're not doing the full displacement, we're doing it piece by piece. So this is our definition of spring force, okay? And we're gonna write that where force is, so that's going to be kx and it's negative, okay? What about so first off, are they parallel, anti-parallel, is there an angle? Parallel, which means the angle is 0, which means the dot product goes away. And instead of r, we can write it as dx because we're only working on the x-axis, okay? Because remember, r is just a dummy variable. It can mean x, y, z, anything you want. But in this case, we know our displacement is in the x direction, so we write this as dx. We also know this is going from initial to final. So what is our initial position? 50. We'll call this 0.5 meters, and our final would be 0. Okay? So, what's the integral of x dx?
X. Say squared over 2.
Yeah, x squared over 2. So we end up with, so let's pull out the negative k, okay? We end up with, so this is just 0.5 to 0 x dx, all right? You can rewrite this as negative k 1/2
x squared from 0.5 meters to 0 meters. And then we can plug in our numbers. So this gives us, and also before we even do the math, do we expect a positive or negative number if we set this up right?
Negative.
So which way is the force pointing? Force points this way, right? The displacement points this way.
Positive.
Should be positive. So we're expecting a positive answer, and if we set up all the math right, we should get a positive answer, okay? And now that you can see there's lots of places we could go wrong. We could forget this negative sign. We could put the integral, the definite integral things, the initial and final, in the wrong place. So it's if you have to get it all right. But that's why it's important to know, just looking at it, that you should be getting a positive answer, okay? So we get negative 50 newtons per meter times 1/2 times, then we end up with 0 squared minus 0.5 meters squared, okay? So you have a negative here, you have 0 minus something so that you get another negative, that should give us something positive. You plug all these things in and you get 6.25 joules, okay? And what is this 6.25 joules?
Energy. Work.
It's energy, it's work done by what?
Spring.
Work done by the spring to get itself back to its regular position, okay? What if you had calculated the work done by you? What do you think it would be? If you, for stretching the spring?
Negative 6.25.
Yeah, if you're holding the spring and it's stretching against you, then it would be negative. But actually pulling it out, right, your displacement goes this way and your force would also go this way. So it'd still be a positive 6.25 joules, but it would be coming from outside the system. So you put 6.25 joules into the system, it uses that to go back to its original position. That's how much energy it expends. That is conservation of energy, right? You have work done by the environment that gives you potential energy. That means stored energy in the spring, and then the spring uses that. And when it's moving, we call that kinetic energy. So it's going to expend 6.25 joules of kinetic energy to get back to its original position. Yes.
Is that why when it was plotted on the graph, it was going this way, but then it would be the opposite, even though the F is pointing that way, your force is pulling, right? So wouldn't it naturally want to pull itself back?
So that's just the force of the spring with respect to the displacement. So remember, the force of the spring is always going to be opposite to, so if you stretch this way, the force is that way.
So
If you
because right now we just found the joules that it takes for it to go back, correct?
Mhm.
So then it takes that exact amount to pull it?
Yes,
Okay.
okay. Any other questions? I know it's kind of confusing, but also a little bit simple. You just have to get used to the basics. Okay, we're gonna do this one together. So this graph shows the force exerted by a spring on a mass as a function of the distance of the spring, compressed or stretched. So this is just a force versus distance graph, okay? It looks a lot like the one we drew when we were adding the spring. We wanna know how much work did the spring do to bring the mass from 4 meters to 2 meters. So what do we wanna do to get that? So first off, is this going to be a positive or negative value?
Negative.
Why negative?
Because it's going in the positive x direction, so the force of the spring has to go back the other way.
It's the same situation as the last time, right? So it's going, the spring is doing the work. So it's already out and it has to go back. So it starts at 4 and goes to 2. So mathematically, if you integrate backwards, right, you're integrating a negative thing backwards, I should give you a positive. From a conceptual standpoint, you can draw it out just like the previous problem where you have a displacement in the negative direction as well as a force in the negative direction, okay? So there's a couple different ways to know this should be positive. How do we actually get the number though? So what are our limits of integration here?
Yeah.
The x equals 4 meters.
Yeah, so we're gonna start here, right? And then we're gonna end here. So what are we integrating from and to?
From 4 to 2.
From 4 to 2. So that means we're going to fill in this space. Okay, so we just need to find the area of this thing. Now, there's a couple different ways to do this. You can either remember the area of a trapezoid, which nobody ever does, or you can remember the area of a triangle and just subtract one triangle from the other triangle. The other thing to remember is this gets complicated because it's below the x-axis, so it's like a negative area, which is a wild thing to think about. But remember, since we know it's positive, we can kind of skip all that. And once we decide we know the sign, we don't have to like be so careful with the math. So remember, the work in this case, we're just going to call the area under curve from 4 to 2. So that's going to be, we'll just do the triangle method. So that's 1/2, right? So that would be this triangle, right? That's 1/2 4 times 4. So that's 4 meters times -4 newtons. And then we subtract off 1/2 2 times -2. Okay, 2 meters, 2 newtons. So once we set all this up, we end up with, this gives us -6 joules, but remember it's a negative area, which is a hard thing to think about. If we want to write out the full integral, the math makes more sense. If we want to think of it conceptually as an integral, then it's important to get the sign from somewhere else, okay? So remember, the position is going from 4 to 2, so work is 6 joules. Okay? And part of the reason for that is that the picture looks just like this. Okay, it's the same picture as before. The only difference is this is going from, this would be 4, and then we'd have some other distance here, x equals 2. Okay? Any questions about this?